Hello, everyone, and welcome to our webinar, Method Validation and Improvement in Robustness of Chiral Analytical LC Methods. My name is Tracy Hartledge. I'm a sales representative and project coordinator for Chiral Technologies and will be your moderator for today's session. Presenting today's webinar is Bill Champion, Senior Scientist here at Chiral Technologies. Please note that during the webinar, you will have the ability to submit your questions as they arise. Please look at the control panel on the right side of your screen and click on the Questions tab to begin. Fielding your questions today will be members of our technical team. We have also placed a copy of today's presentation in the handout section of the control panel. I now turn the microphone over to Bill Champion. Bill, the floor is yours.
Thank you, Tracy. Well, good morning, everyone, or good afternoon, depending on where we are. I'm going to talk about method validation, improvement, and robustness of chiral LC methods. As I put this talk together, I realized I had a lot of information. It was going to be a several-hour talk, so I've had to remove some things or skip over a few things or reference them away. But if you have any questions, this is my contact information. Certainly feel free to contact me later, and I would be glad to discuss anything in more detail. This is the organization of my talk. I want to talk about what our objectives are for the talk, what I hope you get out of it. A little bit about equations, just so you're not too concerned. It'll be fairly simple stuff and things you probably have already seen in a chiral chromatography. There's some special considerations in chiral chromatography, and I want to talk about the validation of the analytical methods, which I think is what most of you are here for, and something that I think is also at least as of much importance is improvement in the robustness of the analytical methods. Then talk about how we can help, and then I'll show you the summary conclusion slide. So this is what I hope you learn from this talk. What we know about achiral chromatography applies to chiral chromatography. So it's not a magic process. It's governed by the laws of nature and the same principles we see in other forms of chromatography. It's a partitioning between the stationary phase and of the analyte between stationary phase and a mobile phase. The complication comes in that we're just dealing with a more complicated stationary phase, and so it becomes a little more interesting, but also a little more complicated. Hopefully some of the things I tell you will remove a little bit of that complication. And so the parameters, equations that we use in achiral chromatography also apply. Chiral chromatography are also often dealing with quantitative analysis of enantiomers at the 1,000:1 ratio, that is 0.1%. Talk about validation of analytical methods. The key is probably limit of detection, limit of quantitation, because we're dealing with a major component and its minor impurity, and we may have a limit of detection issues. We'll talk about selectivity. We certainly need to have separation between the enantiomers, and accuracy, because this is an important analysis. As I was putting this talk together, I realized or was thinking about the things that I do on troubleshooting, and many of the same tests and questions we have in method robustness are issues around troubleshooting. I don't have time to talk about troubleshooting per se, but I did want to point this out. Many of the things we investigate in method robustness are the same kinds of experiments or tests that we would do in troubleshooting. I like to use a systematic approach to method development or to troubleshooting, and so I think I'm going to show you some examples of that. I think what happens is it's a little bit front-end loaded. You do a few more experiments on the front end, but the advantage is you get much better understanding in the long run. Do probably fewer experiments, and it gets you to an optimum or to a good position fairly quickly. It also lets you know how you got there, so you know what parameters are important and maybe what are not. I sometimes deal with people who have a problem with their method, and they have maybe a complicated mobile phase, and I'll ask them about the different components, and they don't always know why they have those components in there, but the answer has come back a number of times. Well, that's the conditions we were using when we found a separation at work. So oftentimes we don't need to use complicated mobile phases or complicated separation conditions. We want to keep the method simple. The simpler it is, the fewer components there are have a problem or to go wrong. So there's the robustness of the method is better generally if you have a simple method. Okay, I have a few equations to show. The things I like about using equations is that they are a succinct expression of the relationship between the parameters and some effect like resolution or retention or something like that. These are fairly simple equations, no quantum mechanics, no matrices, no imaginary axes. And these are all equations that you probably, and parameters that you're familiar with from achiral chromatography. What I would do is I would refer you to fundamental textbooks in chromatography. Even gas chromatography discusses these things in ways that generally are applicable to liquid chromatography. Some of the specifics are different, but we're still dealing with the partitioning between a stationary phase and a mobile phase, and these are equations to describe that behavior. Chromatography is a separation technique, so probably our fundamental equation is the resolution equation, just a measure of how good the separation is. So we can improve resolution by increasing the difference in retention time between the analytes or decreasing the peak width. We can expand this equation. It's just the difference in the retention times of the two analytes, and then some measure of the peak width, such as the arithmetic mean of the two components. We have a divisor in the denominator, so that just comes up as the into the numerator, and this makes a arithmetically more straightforward calculation. There's less ambiguity or confusion about what to do with a 1 over a reciprocal in the denominator. But if we make some substitutions, do some algebra, we get an equation that looks like this. There's several forms of the resolution equation. I would refer you to this. Joe Foley has done, I think, a really nice job of discussing that in this publication. Fundamentally, the equations look like this, but based on some of the assumptions or the ways that you want to make measurements, you may get slightly different terms. I'm not going to go into that, but that could be important. But for our purposes, an equation like this is perfectly acceptable. A couple of things this equation tells us is these are multiplied together. They're independent terms, so we can affect column efficiency, retention, or selectivity independently and improve resolution. So N, or column efficiency, is just related to the particle's diameter. So 1 over the particle size is related to the column efficiency. If you increase column length, you increase column efficiency or number of theoretical plates. Retention factor is a fundamental measure of the retention. Weaker mobile phase gives us more retention. By definition, that is a weaker mobile phase. For example, in reverse phase chromatography, if we have less acetonitrile and more water in our mobile phase, we expect longer retention. Selectivity is a little more difficult because it's more complicated. It's interaction of the analyte with the mobile phase and the stationary phase, and it is affected by temperature. So this is more experimentally driven, so that makes it maybe a little more interesting, but it's less predictable. The greatest effect in resolution in liquid chromatography comes from changes in selectivity, which symbols are usually use A or alpha. Selectivity is most effectively changed by modifications of the mobile phase and or stationary phase, and the temperature has an effect. But as I said, these are independent terms, so we can make changes to each one of these individual terms and affect the resolution without significantly affecting the other terms. And this is a little bit of a problem in chromatography. There is a diminishing return on each of these terms in improving resolution. And this is just some graphs. Since resolution increases as a square root of the number of theoretical plates, if you want to double your column efficiency, if you want to double the resolution, you have to have a 4-fold increase in column efficiency. Or if you double column efficiency, you only get a 1.4 square root of 2 improvement in resolution. Retention factor, and we'll describe the equation of that in a moment. If you increase the retention, the improvement in resolution starts to drop off after maybe 5 or so initial column volumes or retention factor of 5 or so. So if you go from 5 to 10, you double the retention time, but you make a relatively small improvement in the retention, in the separation. Selectivity also is diminishing return. Selectivity, we have to be a little careful that we don't have too much selectivity, because if you have a huge difference in the retention, it just uses up time, and as we'll show, the later eluting peak is usually much broader than the first eluting peak. So there is an optimum for selectivity. These are just some of the calculations of these terms. Retention factor is just the ratio of it's a partition coefficient, the amount of time the analyte spends in the stationary phase with respect to the time it spends in the mobile phase. The total time is the time in the stationary phase and the time in the mobile phase. The time in the mobile phase is really, the analyte moves at about the same velocity or the same velocity as the bulk mobile phase when it's in the mobile phase. So we can substitute T0 is the same time as the mobile phase, and we can't know the time in the stationary phase, but we know it's a difference in the time in the stationary phase and the mobile phase. So this is a fairly simple calculation. It looks a little arcane, but if you think of it really as a partition coefficient, that becomes fairly useful. You see it's dimensionless, that means it's unaffected by column length or flow rate, and so we can transfer this from one column length to another, or one flow rate to another. We'll know about retention factor. Theoretical plates, calculations for these, or the derivation of this is a little complicated. It involves some statistics, but the fundamental issue is the theoretical plates are related to the square of the ratio of the retention time and the peak width. So you can see that the retention time, square root of the retention time determines the width of the peaks. Selectivity is defined as a ratio of the retention factors, but we just can't, everything spends the same amount of time in the mobile phase. It's just the retentions determine how much time it spends in the stationary phase. So this is just a ratio of the time the two analytes spend in the stationary phase. So spend an identical amount of time in the stationary phase, they'll co-elute to be an alpha of 1. If they spend a dramatically different or a different time in the stationary phase, it'll be some number related to that ratio. So if one of them spends twice as much time in the stationary phase as the other one, you'll have a selectivity of 2. And as I indicated, this is the resolution equation. And as we'll see, this is just column efficiency. So this is related to the stationary phase. The selectivity is related to the mobile phase and the chiral stationary phase, and also the retention. These are still independent parameters. It's just that these two changes can affect these parameters differently. And all of these are related to temperature.